So this is the class number 24 of 2020 April, and it is the 8th. We are coming back to this point where we left off. We visit this paper yesterday, Lateral Bracing of Columns and Beam by George Winter. And the brace that we are talking about here is the brace that enhance the stability of structural steel members such as the beam and columns that are prone to the instability. And the instability is the part that reduces the capacity of your members, and you might not be able to achieve to the load that you design if the instability come into the picture before the load requirement is satisfied. So we want to have the framework that is used to determine what should be the appropriate brace design to achieve the capacity of the column and the beam. The point is that, as you know, all the analysis of the steel structures, we need to look into the deform configuration because we are talking about the stability, structural stability. And if you design the brace, well, when you design a column, you know the axial load in the column, right? But if you are working in the deform configuration, you're gonna get the magnitude of the second order effects. If you work on the beam, you get the flexural moment of the beam, but the lateral torsional buckling moment will be incorporated later when you form the second order analysis. But for the brace, you have nothing in the brace, right? If you design for the beam, you get the flexural bending stress. You get some idea about the magnitude, but then you will need to incorporate the instability that is LTB. All right, column you will get like, oh, okay, axial stress will be about this much, but you will need to incorporate the bending moment which is caused by the buckling. But when you talk about the brace, especially the brace which is designed for the stability point of view, you do not have any idea about the force magnitude in the brace, right? Because if you set up everything based on the undeformed configuration, the brace is having nothing in there. Well, unless you have the brace for some other reason also, for example, for the wind, for the earthquake, lateral force resisting system. And if you by chance use this brace for multiple purposes, like for stability point of view and for the lateral applied force point of view, okay, you might be able to find the force magnitude in the brace. But the case that you just have the brace for the stability only, you do not have it for other lateral forces, then you have zero force in the brace. When you have zero force in the brace, you have no idea what size and what cross section, what stiffness that you need to provide to the brace, such that the stability is not going to be the issue for your steel structure. Okay, so here is why this paper come into place. But well, today you're gonna see something which is like different teaching style from the other years, because in former years I teach by following the information available in the paper, but I made decision that I gonna do something which is different, because the thing in the paper can be understood. Well, you just read through, you will understand it. We want to know how much force do we need to provide in the brace. We want to know how much stiffness we need to provide as well, in order to be able to achieve the capacity that we want from the beam and the column. And this is the whole reason for this paper. The thing is that this paper was made in two parts, and I showed you this table yesterday about the experimental program they did in the past, and number of braces increasing, and also the stiffness of the braces also varied in this experiment. Thus, the difference stiffness of the brace affects the load carrying capacity of the column, and also the number of the brace that is provided, which change the effective length of the column, also change the ultimate load carrying capacity of this test column. So we learn from here. We also see that for some cases like this, it shows that the strip broke, and this means the force required from this scenario is more than the next scenario that is able to mobilize the maximum capacity of the column such that the column buckles. But the case above here, as the stiffness you provided for the brace is not as much as the counterpart case. So less stiffness is going to cause you more deformation, and more deformation is going to cause you the larger requirement for the capacity of the brace. So strip broke is just the evidence that shows that less stiffness, you're going to need more capacity. Less stiffness allows more deformation, and as the deformation is larger, deformation multiplied by the stiffness, right, turns out to be the capacity, turns out to be the load. So you need to provide more capacity. This is like quite hectic for the brace, because you need to provide either capacity or the stiffness. Too small stiffness turns out that you need to provide more capacity, and if you provide more capacity, that means your cross section is going to be larger and larger, and then turns out the stiffness is going to be also large. So there will be some number that will be recommended, and all the framework that we are going to learn is a framework that is used for the code writing. So the steel, especially for the stability part of the steel code, written using this. Well, basically, Winter's paper is the fundamentals, and later on I'm gonna introduce you Yura's paper. Yura is my professor. He taught me 15 years ago. More than 10 years. About 13, 14 years. Yeah, when I was in the US in the first year. So Yura is legendary. He's a great guy, and he gives quite a very his thought process is very systematic, and he can put together things and be able to visualize complicated issues in easy ways. Okay, so this is the experimental part that shows the effectiveness of the brace to your steel members, and we come across the derivations in the ideal brace stiffness. The ideal brace stiffness we came across yesterday was about this. If we have the case, if we have the column, and we want to make to increase the column capacity by applying the brace at one point in the middle, pretty much like this. But I would like you to keep in mind that this paper is authored in 1960, and told you yesterday it is already 80 years. We have a state-of-the-art technologies and analysis tool for the design of the brace these days. So I am going to bring you through the different perspective, different approach of the brace design, or the stiffness calculation from the brace by the different view. Okay, so yesterday we first we say that we're gonna mobilize the capacity such that the buckling is going to occur like this and like this as you introduce the brace. So this is the definition of the full bracing. The full bracing is provided and this part buckles and this part also buckle. The buckling load of the system here turns out to be the PE, which is the pi square EI over L square, where the L is taken from this number. Okay, so both parts, the top and bottoms, are mobilizing the highest capacity, which is the elastic buckling load capacity. But in reality, you will not have the brace. Actually, this is not quite correct. It was supposed to be this roller instead of this pin, because the pin it gives you the implication, it gives you the perception that the restraining against the vertical displacement is going to be provided from that pin support, but it should be roller like this. So only the x direction displacement will be restrained only. Okay, but in reality you do not get this roller, which is like a rigid roller support. You have the spring support in reality. So the structure, if you imagine you have the column and then something is going to lock your column against the horizontal displacement, it shouldn't be the ground. Like generally the support is the fixed one, the very stiff one has to be coming from the ground, from the foundation. But something which is going on at the mid height of the column wouldn't supposed to be the real support. It shall be the brace, it shall be some maybe wall and then lean over by some flooring system, and we expect that the given system is going to provide enough stiffness such that the column can mobilize its full capacity. Anyway, and then the derivation was given. It is the simplification, and it is the simplification because at that time, which is 80 years ago, personal computer is not available. You cannot do geometric stiffness calculation very easily because you got to solve like multi-degree of freedom system, which is so difficult things for the people in that age. But we are no longer in that age. The paper is very good for the theoretical development, but I will we finish up somewhere around here, and we learned that the K ideal, I just want you to pick up the number over here, the K ideal, the K subscript ID. K ideal is the 2 times the PE over L, where PE is computed from the unbraced length given or defined above, as I just mentioned. Okay, over L, and the L is also just this part. Okay, so you get the PE computed from this part and divide by the L, which is the length of this unbraced part of the column. It turns out to be the K ideal. So if you provide the spring stiffness to be more than 2 times of PE over L, then you will be able to mobilize the capacity of your column up to the PE. You will have this much load. The derivations or developments you can see in this paper, and I find that maybe I shouldn't continue or I shouldn't talk more about the content given in this paper because it's not going to be new to you. Okay, you can just read through this paper. But for time being, let me check something a little bit. I'm not sure if that interruption of the okay, it is recording. Okay, well, the video was interrupted, and I'm not sure if the recording is ongoing or not, but it looks like it is working. So I think okay, I am relieved with this. All right. In this paper, if you go to the next page, and the paper is already uploaded for you, it is already in the Google Drive. All right, it locates over there, so you just download and take a look at it. So the case that the buckling forms like two half-side curves was elaborated, and then we will see the cases where you have more than that. So you have support at two locations, which gonna form one kind of buckling, and supports at three locations is gonna form another kind of buckling. These calculations are already explained in this paper, so I think I shouldn't spend the time in the class going through all of these details that you can actually read and try to understand by yourself. But the point is that when you come to some this place in the paper, okay, this place of this paper is talk about the K ideal that is actually increasing. It is increasing with the number of the bracing point. So you can see that one bracing point at the middle, your ideal brace stiffness turns out to be 2 times of the PE over L, and then when you break into 3 parts, it turns out to be 3 times. N equals to 3, you have 4 equal parts, 4 equal unbraced lengths, it turns out to be 3.4, and to 5 parts, you get 3.63. All the derivations are given in here. But why don't we try to do something which is more fun than just following these derivations in which is like 80 years ago. Just keep this in mind. I think we are going to do something fun using the knowledge we had in the computer method in structural analysis class. Why do we learn all of those things? Actually, it can be used in advanced steel structure course. So let's switch the monitor to my desktop. Okay, and let's take a look at this thing here. I provide this sort of calculations for you, and okay, maybe first of all, in order to understand everything, you got to look at this, which is the explanation of what we are doing. Okay, so you can see now on this PowerPoint, actually it is the same case as the this one. I switch the monitor back and forth a little bit. It is this one. It is this case. So actually I just cross this out. We focus on this thing in the circle. So I then construct the numerical model into this form, and well, in the paper it said L, but I am gonna put the 0.5 L like this. Well, don't worry, we will tune everything back into the same page. So without the spring, if we run the second order analysis of this column, which is pin and pin, you find that the capacity of this column is going to be pi square EI over L square without 2, okay? Pi square EI over L square. That is the buckling load, Euler buckling load. Well, to be specific, elastic, okay? Elastic buckling load of a column, of which the cross-section is constant and the cross-sectional rigidity is EI. The total length is L. So pi square EI over L square is the capacity, but once you introduce the spring, you find that the capacity is going to increase. And when the spring is stiff enough, what is the stiff enough value? The stiff enough value is value when you have when you are able to mobilize the pi square EI over L over 2 square. That is the value that is stiff enough. That is the K ideal. Alright, so we're gonna play with this problem, okay, and then we're gonna extend into the case where you have 2 bracing point, 3 bracing point, 4 bracing point, 5 bracing points, and so on and so forth. So we will see if the nonlinear geometric analysis is going to give us this same thing. So I bring you to here. The K ideal you don't need to look at this for time being. Okay, what I am doing is first of all I have the P, which is the axial force in the column, and this axial force in the column is given in terms of times. Well, the PE is given by pi square EI over L square, right? The pi square is the constant coefficients. So if I take the pi square out, I have the EI and L square. The dimension is going to be consistent with the EI. It will be consistent with the L. Okay. So I give it like the number of times of the EI over L square, which is like it could be just 0.01 if you wish, to make it small. When we make it small, the number here is like the case where you do not have the axial load in the column, so you do not have the second order effect, and the stiffnesses are provided. So the first part is the linear stiffness of the column, and the second part there is the geometric stiffness matrix. So the linear stiffness is at 12 EI, 6 EI, 6, 4, okay, all of this you know very well. I multiply by L on the equilibrium of the force, then you have EI over L square, EI over L, EI over L square, EI over L, and then I take 1 over L out to the U, so we have U over L, U over L. Turns out that the unknowns here are dimensionless, because theta is the radian, dimensionless. U over L is the length. It is the length scale over the length scale, which is dimensionless. The EI was taken outside, and EI will be disposable because on the other side of the equation, if we run the eigen analysis, the other side of the equation is 0, so EI over L is going to be trashed. And the geometric stiffness matrix you can see over here. It is the P multiplied by 1.2 divided by H, or the length L. Okay, and this is 0.1, which is 1 over 10. You just go back to computer method in structural analysis course and dig it up. Actually, in finite element course, I also showed you the derivation of this geometric stiffness matrix. So you just go and find out how this thing comes if you have no idea. If you take courses with me already, you were supposed to know. If you don't know, something's wrong with you. If you are someone who just pops up and want to know how this thing comes up, just check back into computer method course, all right? And you'll be understanding how this thing comes up. But anyway, the P is coming from here, so I substitute the P as the coefficient times the EI over L square. And as we know that we scale the L and L in these two lines, okay, and we take the 1 over L from these columns, and then you have the U over L into the consistent format with the linear stiffness. So I can put everything together in this form, which is identical to this one. Alright, so first of all, the first one I just showed you here, I have in total 4 elements. I made it 4 elements because if I want to put the brace in the middle, at least in this subsection, so the top column and the bottom part of the column, they both have the middle node, okay, between 2 lateral supports. The middle node is very important because if you want to come up with the accurate prediction of the buckling load, you need the middle nodes. Without this, it will be overly stiff because your finite element does not pick up the point where is super sensitive to the second order effect. So without these 2 nodes, you gotta get higher buckling load, and you shouldn't be glad to get that because your life will be in danger. You have more chance to have a lot of friends in the jail. Okay, if you don't want to have too many friends, keep these 2 nodes. Okay, without these 2, you'll be there. Okay, let me sip some coffee. I need energy. Sometimes I wonder if I prepared a spreadsheet or the note ahead of time and not doing this together with you, it's gonna go with like the light speed. I'm not sure if you like to tune in and see all the things there, and then I just explain very quickly through all of this. Well, okay, so this is provided, and then for this case we have 1, 2, 3, 4 elements and 5 nodes. 5 nodes, 4 elements. In total, you have 10 degrees of freedom. Horizontal, vertical, horizontal, vertical, horizontal, vertical, and so on and so forth. Sorry, not vertical. I just assume that the column is axially stiff, so you have horizontal displacement and rotation, horizontal displacement and rotation, horizontal displacement and rotation. So 2 degrees of freedom at each node. You have 5 nodes. You have in total 10. Now, the restrained degree of freedom are the following. First of all, this is the pin. So rotation will not be restrained, but you prevent this point from moving laterally. Of course, the vertical is restrained, but you do not incorporate this vertical displacement into this analysis because we do not want to know anything about the axial displacement. So forget about it. It is actually restrained too, but it is not included in the system of the stiffness matrix we have. So horizontal displacement here is restricted, and likewise for this point here, it is also restricted. We're gonna see all these boundary condition enforcement in the Microsoft Excel very soon. Anyway, in the Microsoft Excel, I didn't incorporate this spring yet. I am going to do so in Octave. So the eigenvalue analysis later on will be carried out in Octave. Okay, and let's take a look. It is actually better than doing in the Excel, but Excel is just very handy, and you can understand things very easily from this Excel. I'll also upload this Excel on the drive, so you can just go and play around with it. I think at least it is giving you some good understanding before you imagine everything just in the air like I do. So I provide the stiffness matrix from element number 1, 2, 3, 4, 5, number 1, number 2, number 3, number 4. Okay, and then you have 5 nodes. So for the element number 1, of course, I include this is the size of the global of the system stiffness matrix, and then these are the relevant degree of freedom for the element number 1. Others are not relevant, but I provide a space such that when I sum up the stiffness matrix for the system, it is easy for me to manage things on Microsoft Excel. If you do it on Octave, then it is much easier because I don't have to care. I just use the for loop in order to plug things into the right place, right row, right column. Okay, so these element stiffness are actually taken from the linear part and also the geometric stiffness part geometric stiffness part here is going to be multiplied by this scaling factor. I call it this way, scaling factor. So if you see the formula here, you can see that it is this one, and then it is minus this one because the P is the compression. So we have the minus sign and then this point here. Okay, so this minus this one, we have the stiffness that incorporate the second order effect. So this is element number one, and then element number two. Element number two has nothing to do with the first node, rotation and displacement. So this is the element number two. So the DOF here, displacement and rotation here are not relevant. It has the DOF here and here, here and here. This one is not relevant. This one is not relevant. So you have this band. Okay. If you want to understand more, I do not expect any of my students who took courses from the last semester and some FEM in this semester to not be able to understand why the plugin looks like this. But if you are someone who came across and want to understand why the plugging in works this way, then please visit the computer method in structural analysis course, and you're gonna get like a comprehensive, detailed explanation on why the plugging in looks like this. Okay, I reserve the time for steel structure for this, but I will tag this lecture to the computer method course such that this content here is actually valuable to those who are taking that course, which is going to be the next August. But it is actually relevant to that course. Element number 3 and element number 4, okay, easy to plug in, okay. And then finally, I come up with the system stiffness matrix, which is the superposition of element 1, 2, 3, 4, combines all of them into this system stiffness matrix. The point is that for the system stiffness matrix, we need to enforce the boundary condition in order to come up with the buckling load. If we do not incorporate the boundary condition, there is no way to get the buckling load, because you're going to end up with the rigid body motion, and we are not going to get any spurious mode from the column. So like in finite element course that you just I just talked about a few days ago. So you're gonna get only just the rigid body mode. Now, which boundary conditions? So just displacement here and displacement there. Rotation will allow it to be just rotate freely. Okay, so we just remove 2 rows and 2 columns in order to incorporate that boundary condition. So first is this one is the displacement, and this one is also the displacement at the top. Likewise, columns, corresponding columns, and then I migrate everything in the white cells into here, and actually I shouldn't bother shouldn't be doing this. These are from this part here, and the last one at the corner. Here it is. Okay, so I just take the yellow, this yellow out, and I keep only just this part that are relevant in this zone. And then this is in order to find the buckling load, you need to get the P values such that the determinant of the stiffness matrix turns out to be 0. Okay, this is the definition of the eigenvalue problem. So to achieve that, I set here it is the MD term, okay, matrix determinant of the whole thing, and it turns out to be this number. You might not find that it is 0, okay, because we are assuming right now some arbitrary values which is very low. Okay, arbitrary values of the p. Okay, and this is like a zero axial effect from the p. Now we will do the goal seeking. We can do the goal seek, or we can just do it the other way around. The goal seeker is carried out in Excel, because Excel, I try to check. Maybe I should check more that there might be the function for the eigenvalue analysis. There might be, but I think I used to try to check it up, but I didn't find one. So we use the goal seek. So we go to data, we go to the what if analysis, we do the goal seek, and what we want to set cell. This cell is the determinant of the stiffness matrix. To what value? We need 0. Okay, or close to 0, or somewhere that the graph is changing from positive to negative, that is in the vicinity of 0. And then by changing what cell? Changing the p. So we want to know what p value is going to give the 0 determinant of the stiffness matrix, and then enter and enter. So it is seeking for the number. You can see so many iterations. The number might be swinging really crazy. So I just gotta wait for this a little bit, and then there you go. You get the number. The number is what? 9.875 something times EI over L square. In order to make it 9 point something, what is it? Actually, if you think of the Euler buckling load, which is the PE, what is PE? PE is pi square EI over L square. So if I want to write this in terms of pi square instead of EI over L square alone, I want to make it pi square EI over L square. Then this number has to be divided by pi square. Divided by pi square. So here is a thing. This cell is equal to this one divided by pi square. It turns out to be 1.001, which is about 1. The error is about 0.1% by this calculation from away from the theoretical Euler buckling load, because the theoretical one is 1.00000. Okay, but this one you get like 0.1% or 1 in 1,000 of from the Euler buckling prediction. Okay, so this is one way we can get the buckling load using Microsoft Excel. Well, that depends on the goal seeker, and the goal seeker, one bad thing I used to mention is that you have several roots for one problem. So this problem, actually you have how many roots is possible? I think 1, 2, 3, 4, 5, 6, 7, 8. It is an 8 by 8 matrix. Then you can have 8 roots. That means 8 values of p, but the lowest one is going to control the buckling of your column. The thing is that sometimes you might end up with a jackpot, because the goal seeker, I don't never really read into the detail of the algorithm of the goal seeker. So it might slip, it might miss the first, just in case it might. Because other roots could be the solution to this zero determinant, and if you just came across the first root and go directly to the second root or third root, then you are not getting the first buckling, the conservative number. You go to the higher buckling mode, which is not going to happen in the life. All right, the disaster come with the lowest eigenbuckling load. So if you want, it is not mandatory. It is not the homework or anything. You can play actually it is good for you, and it enhances your capacity in the analysis and design of structure. I think this is a very important thing. You can get the knowledge in computer method course to use in the steel in the design of the bracing system of the steel, and we learned something, right? But in the last semester you don't know why we learned this thing. So I think here is going to be the good opportunity for you to really know why we spend time learning of this. Why shouldn't you just run to the field, enjoy the whatever, okay, in the field, rather than just sitting in the N240 and listen to my voice. So here's it. If we want to do it in Octave, we are going to confront this situation. We have the situation where you have the K elastic, K linear part, okay, times U. Actually, the thing is that you have the K minus the P times the geometric stiffness, right, and multiplied by U, and that is equals to the zero vector. Okay. So this is the kind of eigenvalue problem we are dealing with. We are going to get this determinant of the K minus P times G, okay, to be 0. And then what you come up from this are going to be the eigenvector. The eigenvector give us the P values that will cause the 0 determinant of this entire matrix. And we also come up with the eigenvector, okay. So we get eigenvalue first, and then eigenvector tells us the buckling shape of the system. Okay, we can do all of this in Octave, possible, very easy. You have the code. I upload many codes already. You can modify it. If we want to do it in the visualized way, in the way that you can see how things goes, more graphical illustration. Well, this graphical illustration is actually in the modeling, numerical modeling anyway. Then I have the K part, the linear stiffness, and I'm gonna have the G part constructed separately. You can do all this construction in Octave code without spending time doing all this in Excel. You can, but here is for the purpose of showing you how things moves around. So, okay, let's see. First of all, I make it this way. I break into two parts. The linear stiffness is given here on the left, and the geometric stiffness is given on the rightmost. So I take the linear stiffness and stuff it in, okay, and then I also get this part here from the top one. I'm not taking from this one. Why didn't I take it from this one? This one is multiplied already by the P values, and I do not need this technique because I'm gonna find the matrix of P that includes all eigenroots, all eigenvalues. Later, Octave is gonna give me. I do not need the trial and error like this. So I take this, okay, I have the K, I have the G, the P is to be determined. The P here is to be determined, alright? So I do not include it, and then I need just this one. So I take this matrix and then I stuff it into this one, okay? So done for element number 1, then I move down to element number 2, the same thing, I plug the linear part into the right place and geometric part here into the right place, and on and on and on. And finally I get the linear part of the system matrix over here, and I get the geometric part over the right hand side. Okay, and I enforce the boundary condition. So in the yellow are the boundary conditions that I restrain. Enforce boundary condition, I end up with these two matrices. Linear part, I will name it A, and the geometric part, I will name it the B. Okay, and what I have next, I copy this and I paste it on the editor. So it's gonna be here. So I open the A, I open the B. Okay, the A and the B. The A 1.6 something. Yeah, this is it, right? So I am not fooling you around. So this is in Microsoft Excel on both sides of the equation. Both sides. I have the linear part and geometric part, and I enforce the boundary conditions and end up with only just this matrix that exclude the degree of freedom that are restrained. I copy, okay, I copy Control C and then I paste it in the text file. So you can see in the editor the file A and file B are provided in the Google Drive, and they are identical to these things in the Microsoft Excel. So exactly the same. All right, you can see here and there. Okay, so Excel is I took all this from Excel, file A and file B. And file B, I'm not fooling you around. So look at this, 3333. Okay, everything is just copied from Excel. All right, I have the A and the B, and then I just create some some sort of easy buckling analysis root functions. Okay, so I name it buck dim. Okay, file name 1, file name 2, and K, which is the spring stiffness that is to be applied to provide the lateral restraint just there at the midpoint. So okay, I am at this window. Okay, and then what else? I think I closed the iPad. iPad is not needed anymore, so I just get it away from my working space, and we're gonna talk about this the calculations. Okay, so I'm gonna use a lot of computer here. Mostly just the computer screen, not the iPad screen anymore. So okay, you see this system, and Octave we developed over here. I developed over here. So it's gonna read the text file, which is the stiffness matrix that exclude the boundary conditions, degree of freedom out. So A and B will be read from here. File name 1 and file name 2. Okay, the K will be provided later, and we're gonna see how it works out. So the FID1 is okay, from the F open. Okay, this is given when we execute this command. Okay, FID2. So I initialize the matrix A 0 and dimension come from like the 8 by 8. So we're gonna drop in the number 8 over here for this problem. If the problem gets bigger, then we're gonna have the new dimension, and the B of the size of the B is identical to A. So I do the read. The read for the matrix A comes from the file number 1. So the file A basically. So FID1, and then okay, the matrix A was read, and then I read the matrix B as well. So I come down and get the file B.text, and then I get the matrix B. And after that, I have the A44. What is the A44? A44, if you look into this matrix, A44, well, first of all, this is the degree of freedom. This U is at the base. Okay, U and rotation, U and rotation, and U. Okay, so U rotation, these two are for the base. U and rotation, this is for the midpoints of the lower part of the column. And this one, okay, this one, so 1, 2, 3, 4, okay, these are the part of the matrix that you will keep, which is 1, 2, 3, 4. So the location 4, 4 is going to be equipped with the spring. This is the spring that represents the brace. So we are going to vary the spring stiffness, and then we're going to see how the performance of the structure gonna be. Okay, so in the octave here, the matrix A, which is the elastic, the linear stiffness, A44 is that location. Is equals to A44, and then you add up with the K. You need to accumulate. You cannot just A44 equals to K. You cannot do that because you are going to miss the stiffness, which is a contribution from the column itself. Okay, so I add the spring bracing to that midpoint, and then we do the eigenvalue analysis. This eigenvalue analysis, we have the V, which is going to be the eigenvector. The P is for the buckling load, and well, we execute it from eigen A comma B. So A minus the B times what, times B times the P, the eigen buckling load. And then later on I report the P, which is the P11. Well, you will see a bunch of things coming out, but the P11 is the lowest, the smallest buckling load is divided by pi square. So we get the number of times of pi square EI over L square. That is going to give us the idea how much buckling load we obtain from this case. Alright, so come to octave, and then I execute the command. So this is the first of all, the buckling load 8 is the default number we need to plug in order to deal with the matrix size 8 by 8. So A from text file, B from text file. This text file come from what we had from Microsoft Excel. Okay, so nothing, well, you can track back to every single thing. Excel is uploaded, A.text is uploaded, B.text is uploaded, the M file is also uploaded. Everything is uploaded, so there is no reason to be, well, to not be educated. Okay, unless you are super lazy and do not care and do not want to learn, then you are not educated, but everything is provided for you. So there is no reason to not being clever. Well, so I call this one, and without the spring supports, or this one is without the brace at the middle. So we do not expect our column to carry more than just 1 times of the buckling load, and hit enter, bang, then there you go, you get it. So let's take a look. We get the eigenvector. Actually, we can learn from this eigenvector. Our eigenvector here, let's take a look together. We remove the displacement at the bottom node and displacement at the top node, horizontal displacement or lateral displacement. So the first row and first column, no, not first row and first column, only first. Why do we have just this many? It's supposed to be 8 by 8. Did we getting something out? Where is it? Let me check. I think it is a size of 8 by 8. Why is our eigenvalue turns out to be 1, 2, 3, 4, 5? Why is it truncated? Let me check. it turns out to be the right number, but what I want to know a little bit what is going on. I want to see A and B. Save it, even though things turns to be right, but turns out to be right, but okay, it's 8. 1, 2, 3, 4, 5, 6, 7, 8, and 8 as well. 1, 2, 3, 4, 5, 6. Why is it just 6? Huh? What a B? What is going on? 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6, 7, 8. Hey, what is going on with the B? 1, 2, 3, 4, 5, 6, 7, 8. So why? Let's see. The B is dimension. The B dimension is equals to A. Call it. Where is the B? 1, 2, 3, 4, 5, 6. Hey, what? 1, 2, 3, 4, 5, 6, 7, 8. How come? How come? Now funny things going on. CLC first. Clear screen. Call it again. 8 A B 0, and it is the bug. The bug is here. 1, 2, 3, 4. The input argument equals to 4. I have 4. Well, we're supposed to be correct. But why? Well, I just wonder why is the B is just like this. Why is just 1, 2, 3? This one was supposed to be 4, right? For the B. Where is it? 1, 2, 3, 4. Come on. If I do it this way, A B is equals to zeros, dim and dim. Foolproof. Enter. Does it truncate does the program truncate the column here? I guess so. Okay, so it is correct. The output just gets truncated. Actually, there's something on the right of this. Okay, but I don't know why Octave is just showing me just these many columns. We'll see. Command window, file browser, editor, reset default window layout. Okay, forget about it. It is not a big deal. Okay. If someone figure out how to just make the number on the side of this appear, let me know. But we do not need all of them like that. I can do it. Format short. This is a bad way, but it would still not working. Okay, fine. So I execute the command. Let me just shorten it down a little bit like this, and I don't want to see A and B anymore. Okay, it is proven to be working correctly, but it's just a matter of fact that the output is giving out like this. Okay, so actually we have eight modes. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8 degree of freedom. This is the first eigenvector. Second eigenvector, third, fourth, fifth, and 6 and 7 and 8 are not appearing here, but yeah, you can pull them out later. Okay, so this is eigenvector. If you use eigenvector in order to find how the shape looks like, then for example, the first one, displacement is 0, so it does not appear over here, right? Displacement is 0, then the rotation is positive. Positive is going like that. positive is corresponding to the counterclockwise. Okay, counterclockwise is this one, right? It's going to the counterclockwise direction. Come back here. Actually, the program, my program can actually plot it. And then the displacement now, right? The displacement is going to the negative side. So here it is going to the negative side, right? And then what? The slope here is positive slope. Wait. First slope is negative, right? Negative is clockwise. Sorry, right? Positive. Oh, okay, positive slope, and still I think rotation. Displacement 0, rotation positive, displacement which is negative going to the left, and then rotation positive still, but less than this rotation. So it is positive but not as much. Okay, but then when you come to this point here turns out this one is going to the negative, but just a little bit negative. Okay, so the springs just gives you the movement. Oh, sure, this is the first mode buckling. Sorry, not well. 4. Okay, this is 3. This is 4. Okay, this is more. Sorry. Okay, more displacement. More displacement, and this is the rotation. And rotation, you can see that it is close to 0. So more movement, and then the rotation turns out to be about 0. So it is like this. And then you go to the next point. After this one, this is the displacement, which is identical to this one. Alright, 3.18 to the minus 1. Same displacement as this guy. It is symmetry. And then how about the rotation? Minus 1. This is symmetrical to this one. So it is changing to the opposite side, but of which the same magnitude. And the last one is the displacement is not showing up here because we restrain it. Okay, it is 0, and then the rotation is 1.14, which is identical to this top part here. And that is the case. So this is the case where you have the first buckling mode. Okay, this is your eigenvector. Again, the program, I think we have the result shows in the table. Oh, okay, thank you. All right, just read your comment. First mode buckling looks like this, and I intend to bring you through the octave coding for these two parts here. Actually, I provide them, but we'll see if we have much time or not. But okay, let's come across what we want to learn. Now, the 1.005 come from this. We take the P11. P11 is this number, the lowest buckling load, which is 9.8, blah, blah. I divide it by pi square. This is what I end up with. So this is 1. Approximately 1.01 times pi square EI over L square, which is the eigenbuckling load of this particular case. Okay, buckling load of the pin at the top and the bottom, and without the horizontal restraining. Now we come back and see this. So in order to get this scenario where the buckling load if you restrain at the middle point, you want to get the buckling load to be improved, and this effective length, okay, unsupported length turns out to be 0.5 L instead of 1.0 L. Now you're gonna form half side curve here and half side curve there below. So the buckling load is going to be increased, so you're gonna get pi square EI over L over 2. L over 2 as it shortens down your unsupported length to half of this square up, and that's gonna make your buckling length to be buckling load to be 4 pi square EI over L square. 4 pi square EI over L square is your PE. You need to achieve 4 times of the original one. What is the stiffness of the brace that you required? So from the paper, right? You need the 2 PE over L. That is equals to K ideal. So I do the calculation a little bit over here in order to find the K ideal. Okay, how much K ideal we need? So 2 times PE. So PE turns out to be pi square EI is the scale of 1, right? Pi square EI over L square. And L square, this is the P, right? And when you want to K ideal, you got the PE divided by L, another L. And what are the L that we are talking about? The L we are talking about is 0.5 L, according to the definition we had for the K ideal. K ideal is computed from this unsupported length. So it turns out to be 0.5 L. So the L cube is down here, okay? And we get the 157 times EI over L cube. So once we put the load to, put the spring stiffness to this much, we must be able to achieve the load PE, which is equals to 4 pi square EI over L square. Okay, you got it, right? Now we come back here. We come back to this picture, and then we add in the lateral stiffness of the brace. So start from, make it 10. What is the goal? The goal is to see the answer here to be 4 times. We need to see the number 4. When you get the number 4, that means your brace is the full bracing by definition. It enhances the capacity of the column to be equivalent to the case where you have the real support, which is the non-deformable support. Okay, so I hit this is 1.2. Okay, we add some stiffness there. You get the improved capacity, but it's not as good. Make it 50. You get 2 times, but 2 times is not the target. We need 4 times. 100. Oops, sorry. No, we need just 100. 100 make it 2.9. Further, 150. 3.8 times, not 4 yet, right? Finally, what is the number? We need 157. So 157.9. Okay, I make it 157. Okay, 3.9944. We are close. 158. We get 4. Now 170. Let's see what are we going to get. It's not better. Actually, the number, the rounding here is insignificant, but you still get somewhere around 4. Make it much bigger, like 1000, like we did before. it stops at 4.03. Basically, it is just the buckling, elastic buckling load of this part here, the top part here. So you go back, you can try check this eigenvector and try to plot how the the buckling shapes looks like. Okay, but actually it's gonna be like the shape, the curve like this, and this curve here, no matter how much stiffness you put here, you put 1, 2, 3, 4, 5, you can see the improvement. And then once you are hitting the number of 157, 158, you hit the limit. So it is the full bracing condition, and you will no longer get the improvement or the increase of the column strength because it's gonna buckle in this shape and it's not going to be higher. Okay, so here you can see the consistency of the theoretical development in Winter's paper and also in Ura's paper, that the K ideal is proposed. Well, in reality, you will not just pick K ideal, because in the design point of view, you will add something more. This is the ideal condition. Ideal condition is corresponding to the case where you do not have the initial out of straightness. Zero initial out of straightness, which is not realistic. In reality, you're gonna have something, okay, which is not just this. Well, actually, we can play with that. I try to construct the code, but it's not done yet. Actually, it is here. So if I just manually change and introduce the out of straightness, initial out of straightness in the code, it is possible to see how the response of the structure is going to look like when we have initial out of straightness. It is fun to do. It can be done. All right. Actually, you can do it ahead of me if you really want to. So this is the first case. And then we end up with the figures that match exactly with what is proposed there, which is 2 times of the PE. Okay, 2 times PE divided by L. Now we can move over to the case where we have the 3 segments like this, and the paper said that you're going to need 3 times of PE divided by L. That's from theoretical derivation. So we'll see how it's going to be by our calculation here. So I can just duplicate the picture, this one. So this is for 3 elements. For 3 elements, I will only have to add 2 more rows like this, insert, and over here as well. Oh no, not just 2 more, it has to be 4 more. 4 more because you have 2 more nodes. 2 more nodes. Each node has 2 degrees of freedom, so in total you have 4 more. Then I give it a little more in sphere 1, 2, 3, 4 like this, and we need 4. Oh, why is it slow? 1, 2, 3, 4. Insert 1, 2, 3, 4. Insert. Actually, it is gonna be better to use 2 PC. 1 PC is used for live, another PC is used for the calculation, because I think that the graphic card is a little slower, not a little, it's a lot slower than it used to be, and that is because of the simultaneous operations going on in the computer, in this same computer. Life is going on and calculation is going on. It's too much for a computer to handle. Oh no, it was supposed to be a file. When we can bridge the knowledge learned from one class to another, I think that is a very good feeling. Okay. So, okay, no, we don't need to do anything with that. Element number 1, number 2, number 3, number 4, we need element number 5 and 6, so I'm gonna spare this space. Insert, there it is, remove clear formatting, and slow. Element number 5 and element number 6. Okay, I delete everything. Delete. Okay. Number 5 and number 6, just copy it. Copy and then paste it on this side. So we're gonna need we're gonna need a few more paste. Okay. Okay. 1, 2. This is for the last element. This is for, okay, this element, the first one here is going to be equal to, okay, let's take the part here, enter. Actually I can take it from above because the element size is made to be the same, 4 by 4, that's it. And this one, 1, 2, 3, 4 is equal to this. So copy and copy, and that's it. Easy, right? And now for this one, let's see, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. There it is. I equate this to this one, same stiffness, and there it is. And yeah, this coffee spill over myself, smell like coffee now. Is the internet working? It looks like the internet doesn't work. Online teaching is relying on the internet mostly. Okay, so 1, 2, 3, 4, 4, and that is equal to this. Yeah, okay. I'll just go ahead. I don't know if it is working or not right now. I am tired of it. Delete and delete. So I have the system stiffness. All of this could be very easy if we write the program. The first column here, this one here, this one here, and this one here have to be removed out of your consideration. Okay, so I just include this. Okay, 16. I need the 32 down there. Okay, yeah, that's just right. And it is okay. Adding. Okay. Here you go. And that is going to be the same. So I can just copy this one and paste it there. So we get the same thing. Yeah, just like this. Then we need a little bit of things to do. This one is for the 3 elements. The size is not 3, right? This is 0.33, 0.33, 0.33, add up to 1.0. This is 0.167, which is, this is 1/6. So I got to come here, and L is equals to 1 divided by 6, and this is it. 1/6, and the new matrix we can come back to Octave and we make a new file. It's just a text file. I make it name what A2 and B2. Okay, so let's take a look at A2 and B2. A2, copy it and paste, save it, and B2, copy it and paste, and save it. Okay, so how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12. So we can execute, but first of all, the this is changed to 12. A will be A2, B will be B2. 0 spring stiffness first. Okay, here we go. We get 1.0 now because we do not put any spring in there. If we want to restrain this case that you are having to spring, so this is the 1, 2. Okay, the 1 is gone, so 1, 2, 3, 4. Okay, number 4 will be restrained. 1, 2, 3, 4, 5, 6, 7, 8. That means A44 and A88, and they are going to be restrained. and then save it. So the spring here, it used to be 2. Right now it has to be 3 according to the derivation given in the paper. And 0.5 is not going to be there anymore. It has to be 0.3333. 0.3 and 0.3. So now it turns out to be 799. If you have 799, then you'll be able to produce the buckling load that is equals to 9 pi square EI over L square. Okay, that's the meaning. So we have all this. Then you can add the spring stiffness 50. You get 2. You can do like a 150 previously. You get 5. Okay, still not 9. 300. You get 6. 500. You get 7. You still need 9, right? 700. You get 8. What is the number? I think 900, right? 799. Oh, okay. 800. 9. Okay. And what if we have more than that? So make it 1000. 9. Make it 3000. You get 9. So you are saturated somewhere, and that point you get saturation is the point where you get the K ideal, which is 3 times of the stiffness, 3 times of the stiffness, which is computed from PE divided by L. That's the thing. So the computational aspects we developed in-house, it is actually consistent with the proposed theoretical development 80 years back very well, but it is quite very easy for us to we have more flexibility to study into various cases. For example, actually these are also proposed in the paper, but we can do it in the easier way. For example, if you want to have maybe just this, so you have the upper part being 0.66, 0.67 L, and the lower part is 0.33 L. So you might need to know how much spring stiffness which is required in order to achieve the maximum possible buckling load of this system. If you want to do it in the theoretical development, like in Winter's paper, it is possible. Okay, you go back, look into this paper by Winters and by Ura. I will upload Ura's paper too. You will find a way to achieve to compute this spring stiffness. It is possible, but with the computer software we developed it in the class, or even in Microsoft Excel, the easy one, in Octave, whatever, you can come up with the brace capacity. Okay, the brace stiffness, required stiffness from the computational tools we have. So this is actually more worthwhile than the paper we look into, or the paper that are the baseline, that are the fundamentals of the code development. Okay, we have many possibilities to play, and please use of that. So we will later on in the next class we will talk about the paper which is written by Yura. Yura is going to introduce you the initial out of straightness, and then we will also try to play with that initial out of straightness with the code that we see that it works very well. So we can play with the code using our code, and in order to compare with the paper by Yura. That's gonna be a lot of fun. So I think we'll finish up this class for today. We have many rough situations going on today, but we finally make it. So I will upload all these materials on the drive, and you can play with all of these with your by your own. Okay. All right. Then let me wrap up this class over here. Have a good day. Bye bye.